let's get started. Before I begin today's discussion, I want to remind you about factory tours. So every year about this time, as we launch the second part of the class, which focuses more on system level issues in manufacturing, we offer the opportunity for you to go see your choice of local manufacturing facilities. We hope that you will be able to attend one of these tours, and of course we make the usual email announcements, but I wanted to mention it in person. This year we actually have a more exciting and diverse set of choices than before. The first one is tomorrow to Amazon Robotics, formerly known as Kiva Systems. They are the part of Amazon that makes the floor vehicle robots that move the shelves around inside warehouses. So on the first lecture I told you about how in Amazon's warehouses and warehouses of many other distributors, your package of things, whether one or many, is packed by humans to whom the shelves are brought. And you will see their test area. I've been there before, where the robots run around and get tested out, as well as see their manufacturing and assembly line, where they put these vehicles together. And a lot of electric motors, some big CNC machine parts, some wiring, and so on. Then next Wednesday there's a tour of GE Aviation, a local facility where they manufacture and test engines for the F-14 fighter jet, an older fighter jet but still being produced. And unfortunately, if you're not a U.S. citizen, you can't attend because it's a U.S. government contract and they make that restriction. But if you're able to go and interested in aviation things, you'd see a lot of sort of more high-end specialized manufacturing assembly, especially I think a really nice machine shop for doing CNC machining. And then 2 days before Thanksgiving, week of Thanksgiving, we have a tour of Nipro, and we've been to Nipro for many years, and they're a huge company that does a lot of injection molding, automated injection molding for healthcare and consumer products. They're actually owned now by Jabil, which is a multinational company that does a lot of contract manufacturing of electronics, and that's the third option. We really hope that you can choose one of them. If you cannot make it, or choose not to make it, Dave Dow asks you to complete something in exchange that tries to express the principles that you would see in a tour like this. Always note the meeting location 10 minutes before the tour departs. Also, we know that per MIT rules we can't and shouldn't obligate you to things between the 5 to 7 p.m. window, so we just want you to be aware that if you go on a tour you might be coming back late, especially to GE Aviation because it's a bit farther away than the others. And of course if you sign up we expect you to attend. I know things come up last minute, but we expect your sign up to be what you'll end up doing. Yes?
If we fill in the Google form, are we going to get any kind of like confirmation that you're like...
Get a confirmation that you're going.
Okay. If
we haven't done that, we should do that. Hayden will, or Dave will email you all and say, hey, yeah, we'll see you on the tour. Thanks for asking. Any questions on that? Okay, so today's subject is manufacturing cost, and I appreciate that you're all here. I know 13 and a half hours after a quiz, you're not necessarily feeling like jumping back into the class again, but I like to get started right away, and cost is a really interesting and important subject in manufacturing. It's, in some realms a more businessy thing than technical thing, but it's really essential to understand and plan manufacturing processes. And I hope by the end of today we'll have a lot of nice examples and observations, as well as a framework that we can use to estimate manufacturing cost. Cost applies to everything that's manufactured. Coffee that you might make or get every morning contains multiple parts made by multiple processes. Some that we've discussed already, like thermoforming. And if you think of the supply chains for these elements of the product that I buy in Lobby 7 for $2.50 or thereabouts, there's many handoffs in that process. Even the coffee beans that are grown often in another country and cultivated and harvested and roasted and then sold to the place where you buy your coffee in the morning. There's many different chains in it. And then on this slide I have a diverse set of products. What can you say about what might drive the cost of manufacturing and perhaps the cost of sales of any one of these? Yes?
Cost of materials.
Cost of materials. Which one might be more driven by cost of materials? The metal ones? Okay, yeah, metals are generally more expensive, maybe high-end metals for medical implants. What about glass, window glass? Is that going to be heavily material cost driven? Yeah, I think so, because it's big and heavy and made out of earth. Glass can be highly functional, as I'll describe later on, but that'll be material cost driven. What are some other observations about what's here?
Scale?
Scale, like production volume, sure. I mean, cost is always a function of production volume, no matter how you make it. If you make it by hand or you make it in a highly automated fashion. Something else? Do you have a comment? Or?
That live chicken has a cost.
That live chicken has a cost, yeah. Of course, the cost of raising the chicken and you know, whatever the chicken does, lay eggs or something else. Actually, what I put this on for was the jacket, the reflective jacket for the chicken. So you can actually buy a chicken jacket. So if you want your chicken to be safe when it crosses the road, or you buy the chicken a jacket. I saw this in a UK newspaper. Seriously. Here's a product where, you know, maybe the production volume is low. I don't know how big the market for chicken jackets is, but the profit margin is probably high, because if you want to buy a jacket to protect your chicken, you are probably going to pay a pretty good price to protect that chicken. Same thing to protect yourself if you need you know, implant surgery, right? Medical devices often are certainly very costly to manufacture and certify and make sure they're safe and sterile, but also high profit margins on high-end things like medical implants. You know, we see Gillette razors, the blades themselves made in quantities of many, many million, you know, sort of ultimate cost, asymptotic cost at high volume. And then we'll talk about consumer electronics and the phone cases. What do you think is the profit margin on a simple phone case? Super high. Yeah, it's ridiculous, right? You could pay $10, $20, $40, $60 for a phone case. Might be a simple $10 one that's just a frame by injection molding. By the end of the day, you might say that might cost $1 to make or less. So huge profit margin, cost imparted by the need for it, right? You want to protect your phone is valuable, and also a bit of the fashion and aesthetics that you would prefer. As we go into the next few weeks, we're also going to talk about manufacturing of electronic devices. We will follow the example of the Amazon Fire 7-inch tablet. So this is a low-end tablet computer, 7-inch screen diagonal, you know, you get it in the packaging. Packaging's multiple processes, nice printing. It's shipped to you. You know, has all the functionalities of a decent yet low-end tablet computer. And if you take it apart, you can learn about how it was designed and manufactured. So you see the back case, injection molded. In fact, it seems that these parts, we took this apart late last year, where we worked individually. It was when they just started selling it. And then you see the battery, and you see the circuit board assembly with under this shielding is the processor and communication. And then you have the touch screen, and the screen is decent resolution, right? Has special films on it to be able to sense the position of your finger. This is a highly complex product that results from mastery of an immense number of processes, from the finest scale to the full scale of the product. And by discussing manufacturing cost and discussing electronics manufacturing, we're going to appreciate a lot of things that go into this. So when you get the next homework assignment that will be due a week from tomorrow, that's homework 6, we're going to set you up with a page of motivation that talks about this product, and we'll build the subjects of the next 3 homeworks with the Amazon Fire as kind of a case study. And when I first saw this, I was really shocked. They sell this for $50. They still sell it for $50. And, you know, in a way, we're really used to electronics being ubiquitous and everywhere, and now, you know, computation power and screens are getting cheaper and cheaper. But I was really impressed by the fact that they can bring this product to market and sell it at such a low price. And you know, they use it to deliver content. They want you to sign up for Amazon Prime Video and buy stuff on Amazon, so there's probably something there. But it's really impressive that this can be made for probably a cost of tens of dollars or so. So, you know, when you think about manufacturing cost, we can first think about the cost of finished products. And one of the ways we define manufacturing early on in the course is that manufacturing is, you know, adding value to raw materials. This is a nice chart from Ashby, the same Ashby who made some of the charts that I showed in the process selection quiz review discussion. And he's going to be our go-to reference for understanding how to model cost. And basically, he does this nice banding and ranking of price per unit mass of a wide range of products. At the top end, you have really valuable specialized things like contact lenses. You don't always think of contact lenses, if ever, in the cost per kilogram, but a contact lens might weigh a fraction of a gram and cost at least a few dollars for a disposable one, and you might get a cost of $100,000 to $1 million a kilogram. Now, I'm sure that's way more than the cost of the raw materials, even if the raw materials are specialized. Going down to the bottom left, the lowest cost product is a parking garage. So if you want to buy a parking garage, you can buy it for about 20 cents a kilogram. Anyway, in between various levels of raw material intensive products, all the way to highly engineered products. And you see that based on the sophistication of the product and the specialization of its function, the final cost goes up. And we end up in the top right with high-tech products, whose competitiveness is linked more to performance than cost, like contact lenses improving your eyesight, heart valves, saving you from heart failure, hip implants, commercial aircraft, things like that. And there are many factors that influence the ceiling, the maximum amount that a manufacturer can charge for a product. It can be the market size, it can be the value to the customer, it can be whether the market is competitive, and it can also be brand equity, right? People argue, are Apple's products really as good or better than their competitors? In some cases, technically no, but they have a huge brand equity because they have devoted followers who really like buying their products and the experience of using them. That adds to their ability to cost. So if you study business or marketing, you might take a course on the process of and the psychology of setting prices. That's not what we're going to get into, but we want to understand what enables you to set a price based on the cost of manufacturing something. So what do we want to understand today? Well, we want to understand the answers to these 4 questions. First, what are the elements of manufacturing cost and product cost? Once we've overviewed those elements, we're going to learn how we can predict, estimate the cost of manufacturing a part at large volume. Then we're going to talk about, by some examples, what differentiates the cost of different manufacturing processes and how is manufacturing cost reflected in the cost of a product and how different companies operate. So putting those last 2 questions together, we can look at products and companies that do fairly raw material intensive things or fairly brand driven things, and if you look at their financials, like go to Google Finance and look at their stock price and go and say, well, how much do they take in revenue and what's their profit and what's the profit divided by the revenue, it's really interesting to me at least to look at the differences and reflect back on the nature of their manufacturing operations and the nature of the products that they make and sell. So according with this, we have this agenda. We'll break up manufacturing costs into fixed costs and variable costs. We'll go through an example, the cost of making our good old Lego bricks, and we'll talk about those limiting examples, products, processes, and business models, and then we'll conclude. So, say more things. What contributes to the cost of manufacturing something? Someone said cost of material already, obviously. What else? Yes?
Like how difficult was the design?
How difficult it was to design, yep. So the cost of design is very important. Yes?
Cost of production.
Cost of production, what do you mean?
So however much, like if I wanted to make a lot of things that were injection molded, how much it would cost me to use the machine that so company.
Yeah, so cost of the machine or cost of using the machine. What else might go in the cost of that?
Labor cost.
Labor cost, yeah. What else are we missing for injection molding, for example? Tooling, yeah, tooling cost. Anything else?
Like safety equipment here?
Yep, safety equipment, what it takes to run the factory. Overhead is one way to call, to say that, maintenance costs. Yeah, so I think we got pretty much all the elements, and this is the way we might break them down. We'll talk about material cost, equipment cost, tooling cost. That could be mold cost for injection molds, or it could be the cost of milling tools if you're CNC milling. Labor, and then an additional category called overhead, which might include energy, equipment maintenance, facilities, say extra employees that you need to operate your facility or oversee safety. And you mentioned very correctly that the cost of research and development, engineering, design, sales, and marketing are very important. We actually won't include them directly in our analysis of manufacturing cost, in our cost versus volume, but it's important to appreciate that every product has to be designed, and there is often a research budget and a design budget and an engineering budget, and the costs of those elements of the process need to be considered when a company makes a decision to bring a new product on the market. So we'll talk about the cost versus volume of manufacturing, but if you think of what makes a viable product for a company, they have to consider the cost of all those operations. And, frankly, the availability of greater, more global contract engineering and manufacturing services makes this process of planning manufacturing cost and executing design and manufacturing projects much more flexible. Flexibility in being able to more easily scale the amount of resources that you have access to, right? It's a big difference if you're able to, ask someone to injection mold your parts for you and get them quickly in the quality you expect according to your specifications, rather than have to buy an injection molding machine yourself and learn how to operate it. Or even if you are masters of operating injection molding yourself, have to maintain that facility for a long period of time. So cost structures can be more or less flexible, and that's an important sort of global consideration to keep in mind. So we're going to adopt Ashby's simple model for estimating the total cost of making a part, of manufacturing a part. And I will start from what is in the chapter that we post for you to read. And he basically says you can break down the total cost of making a part into the following categories: materials, capital, capital investment, where he says that's the cost of tooling and the cost of equipment, the cost of time, labor, administration, rent, the cost of energy, and the cost of information, which he says is R&D or royalty payments. That excludes sales and marketing. So, I feel that to introduce this process of cost modeling, the chapter from Ashby and what he says about cost is the best reference that I know of. And he categorizes materials, capital, time, and energy. But what we're going to do is the following. We're going to say we're not going to worry about the information cost. Just keep that in mind, that exists. We're going to consider the cost of materials. We're going to consider the cost of tooling and the cost of equipment. And then we're going to group all of these into one category that we're going to call overhead. So overhead, in our estimation, can include labor, energy, administration, rent. It's kind of like difficult and context specific to estimate those. So we're basically just going to lump it into the cost of overhead per hour or per part. And how do you calculate the total cost of making a part? Well, you calculate the cost of each component and you sum it together. And you just have to be conscious of the units that you use. And basically what we're going to do is we're going to present a way to estimate the cost of each component when you manufacture something as a function of production volume. So dollars per part versus N, where N is the production volume for material, for equipment, for tooling, and for overhead. And then we're going to sum it together, and we're going to be able to derive this function of cost versus production volume for something that we make, such as a Lego brick. And the classical curve in modeling manufacturing cost is the one that I use to introduce cost as one of our four process performance metrics. The idea being that as you increase your production volume, and this could be total units in the history of what you want to sell, or more commonly we might say total units per year, the cost per part, cost per unit, C divided by N, goes down. And this is just a simplified representation to show you how the cost declines and reaches an asymptote. And the high-level idea is that you have both fixed costs and variable costs. Fixed costs are the one-time investments that are needed to start up manufacturing, like machines, like tooling. And variable costs are the costs that you have to pay every time you make something. So imagine you were able to say, every time I make a Lego brick, I have to pay this very, very tiny increment of labor. Or of course, for every Lego brick, you have to use an increment of material. Those would be the variable costs. And if you look at the asymptotic limits of this representation, then if you have a production volume of 1, the smallest possible, then your cost is dominated by the fixed cost, right? If I need to injection mold 1 Lego brick and I have to buy an injection molding machine and buy a set of tooling, then I have to make that fixed investment. Yet if I want to do an infinitely large number of bricks, and I can divide the use of that machine over all of the bricks and the use of the tooling over all of the bricks, then at an asymptote my cost approaches the variable cost. And this is exactly what we see, however I'm really explaining extreme limits, right? You would never buy an injection molding machine to mold just one part. Likewise, if you mold an infinite number of parts, you're going to need many machines and you need many sets of tools. So what we will do is equip ourselves with a methodology to be able to do a more exact example. But this fixed versus variable cost trade-off is what people think about when planning production volume. Certainly this is something that the advent of new technologies such as 3D printing can start to challenge. But the cost dependency of 3D printing is a more intricate subject that we won't talk so much about except for an example at the end of today. So tell me what this slide represents. So this is schematic cost versus volume curves for, say, different levels of automation in a process. Could someone explain this to me in another way? Like why is one curve higher higher in cost at high volume and another curve higher in cost at low volume? So imagine one of these is a highly automated factory and one of them is a highly manual factory. Which would be which? Yes?
Manual factory is going to have a lower cost at low volume, but a higher cost at high volume.
Yeah, so right on. So a manual factory is going to have a lower cost at low volume and a higher cost at high volume. So now that we explain it, it may seem pretty obvious that that's the case. And I use this illustrative example to say that when you think about designing a factory and a manufacturer thinks about designing a factory, often a consideration is how automated do you want to make the operation if an automation requires additional capital investment, additional fixed cost for a highly automated operation, yet allows you to reach lower cost at large volume. So consideration of target production volume, market analysis to know I can sell 10,000, 100,000, a million, 10 million, reflects back on how you design the factory and what sophistication of processing or equipment. Same thing of like prototyping versus mass production if you would be 3D printing versus injection molding, for example. So Ashby's chapter talks about this a little bit, and he actually says this can apply to the example of sharpening pencils. So maybe a post-processing step if you're a pencil manufacturer, and he uses the example of saying, well, you could sharpen with a knife, and therefore, it doesn't cost you anything to invest in an electric pencil sharpener. Maybe it's the cheapest way to sharpen one pencil, but if you need to sharpen more and more, you could go from manual pencil sharpening to automated pencil sharpening. And if you ever need to sharpen a lot of pencils, I found that Alibaba provides you a way to buy an automated pencil sharpener that can sharpen 200 pencils a minute. So I guess if you buy pencils and they're pre-sharpened, you may have a machine like that in your factory. You can find pretty much anything out there when it comes to making stuff. So if there are no questions right now, let's get into the different cost components. I think this is going to be pretty straightforward in terms of the mathematics involved, the formulas involved, but if we take it carefully, it'll give us a perspective on what goes into each component of manufacturing cost and how that scales across. So first I'm going to treat the fixed costs. Our fixed costs are cost of tooling and cost of equipment, and give you a few examples. This is an expression that tells us the cost of tooling for making a part. And the idea is that this is our first cost component, so we're going to call it C sub 1. And the C sub 1 is going to be in units of dollars per part. The expression says that we calculate the cost of tooling per part by looking at the cost of one set of tooling. Say this is a set of molds for our Lego bricks or for your yo-yos. We divide it by the total forecast production volume, say we're going to make 10 million parts, 10 million yo-yo parts or 10 million Lego bricks. And then we multiply it by an integer function, which is the ratio of our total production volume divided by this small n, which is the number of parts each tool set can make before wearing out. So what does this tell us? That you must have an integer number of tool sets. The tool sets can't be used to make other parts. And for example, if you know your tool set is going to last for 1 million parts, and you need to make exactly 10 million parts, or try to make exactly 10 million parts, then this would tell you you're going to need 10 sets of tooling, and your manufacturing cost of tooling per part can be divided as such. If you need to make 10.1 million parts, and each set of tooling makes 1 million parts, then you're going to need 11 sets of tooling, so that's why it bounces up, jumps up the integer function here. This assumes that the tooling is dedicated to the project, and we're treating this sort of independently from what your production rate is. What I mean there is, like, I could say, well, I need to make 10 million parts and I need to make 10 million this year. Then if each machine can only make 1 million parts in a year, then I, have those 10 tools operating in parallel in 10 machines. If I can make those 10 million parts over 10 years, then I only need 1 machine and 1 set of tooling in time. So this is an abstraction, but it's just telling us how much of that fractional cost of the tool we have to pay for each part we make. And of course, we can appreciate that mold tooling can be quite simple and made out of lower cost materials like we do in our shop, all the way up to very expensive, intricate mold tooling made for complex components like housings of electronic devices, or even like the front case of the tablet here, where we're seeing our rule of uniform wall thickness be practiced, but there's a lot of ribbing for structural rigidity and bosses here for holding. I think this is where the camera is placed, for example, and so on and so forth. The way that you determine the cost of tooling, or a toolmaker calculates the cost of tooling, is based on all these things, like 2-plate versus 3-plate, and whether there's integrated cooling features. But there are some simple scaling observations that we can make to understand how, tooling cost scales. And in fact, one way to understand that is to simply go online and manipulate a mold cost estimating application. And there's a couple that I'm most familiar with. One is this on this website called Custom Part.net, which is just a nice website with manufacturing information, and basically lets you input a lot of rough data about your mold. What is the envelope of your part? What's the projected area? Do you have projected holes? What are the tolerances you want? What's the surface finish? What are the complexity options? And this is totally qualitative. And then it has some aspects on the mold class that we're going to define in a minute, the number of cavities in the mold, and the labor cost of making the mold. So what this has is just an algorithm behind the scenes that takes into account these variables of your mold tooling cost and comes up with an estimate. So what did we do here? This is in millimeters, so we made something that's prismatic and roughly the size of a yo-yo part. We said it was to be of a particular mold class, class 103, as we'll see in a minute. It means that the mold should last up to 500,000 cycles. And we found that the mold cost estimate would be about $10,000. Just a number right now, and you can explore this on your own. In fact, in the homework, we'll ask you to use one of the other calculators, which is from Proto Labs. Proto Labs, the company that gave us the plastic cubes for the injection molding homework. Their business is doing custom short-run injection molding, and you can send them a CAD of your part, and they will tell you what the mold tooling will cost, and they will tell you what it will cost to get molds made. And they have different configurability options for the mold tooling. This mold class is something that's defined by the Society of Plastics Industry, so the organization of plastics manufacturers who can agree on a standard that everyone can communicate. It's a bit weird, like I don't know why it's class 105 down to class 101 and why the numbers are inverse to lifetime, but basically a class 105 mold can be made actually, just for prototyping, can even be made out of soft cast metal or epoxy, all the way down to a Class 101 or up to a Class to 101, however you look at it, which is rated for more than 1 million cycles. This requires extremely hard tool steels and hardening of the mold material. And this is a specification on Rockwell hardness, a measure of hardness of the tool, because hardness is important because molding requires high pressure and repeated pressures over that 1 million cycles are going to fatigue the material. So you need a natively hard material in just the way you think of a milling tool requiring high hardness, where instead of the cyclic cutting operations, it's the cyclic pressurization and depressurization and heating and cooling that cause the mold tool to fatigue. Class 104, incidentally, an aluminum or mild steel mold can last you, if made well, up to roughly 100,000 cycles. And this is, of course, very part and case dependent, but this is a classification that's used to adopt standards. And if you use the calculator that I showed you the screenshot of, you can actually keep, what we did is we kept all the parameters of the mold the same, except we just we only adjusted the part size, in this case in cubic inches, and we found that as a function of the number of cubic inches required at this medium mold class for a cube-like part with 2 cavities, we found the cost to be increasing, of course, with part size, but sublinearly increasing. What does this tell us? Well, there's some fixed cost itself to buy the mold, to make the mold, and then it costs more to have the mold be bigger because you need more material and you need more time to machine it. So it's even like a scaling law within the cost dependence of each of these elements. What I mean by that is, there's a dependence of the cost of tooling and the cost of machine based on the size and performance of that. And then the influence of that cost on your production process will depend on your production volume and other aspects. Okay. Are there any questions on the tooling cost? All right, so the second fixed cost element is the cost of equipment. So the cost of equipment is, of course, for example, our milling machine or our injection molding machine. We have another small equation here. C2 is just my definition for equipment cost, and this is now the cost of equipment that we have to pay for each part that we make. The formula is the following. Let's start in the middle. So C sub M will be the purchase cost of a machine. Say it's an injection molding machine, costs $100,000. L will be what I call the load factor, so the fraction of time during which the equipment is productive. What could go into that? Well, how many hours a day your factory is open, and moreover, how much uptime the machine has. So for example, if the machine is only working 90% of the time, is down 10% for maintenance or whatever, you need to include this load factor. TWO, write-off time, is simply the lifetime of the equipment. So what this means is if you buy a new machine and it lasts 10 years, or you expect it to last 10 years, then you divide the cost over a 10-year period. This is a very simple way to handle what's called depreciation or write-off of equipment. Finance folks get much more detailed in effective interest rates and cost of money, but this is simple enough for us. And then you take this formula, which basically tells you what is the effective cost of owning this machine per year, right? Total cost of machine divided by number of years divided by load factor, divided by 0.9 would increase the cost if you have 10% downtime. And then divide this, or multiply it by 1 over the production rate of this one machine in parts per year. So if this is how much it costs to own the machine for the year, and this is the number of parts that you can make in a year, then this is the cost of each part that you make. And this is one formulation for that. Yes?
So why does L not encapsulate within N dot?
You could. It's just a matter of convention.
So N dot would be like the maximum of the cost we make, and then L is like how it goes.
Yeah, so exactly. So say I know my cycle time is 10 seconds, and I know my factory is going to be open for 16 hours a day, then I might say, how many parts can I make 16 hours a day times 365 days a year at 10 seconds cycle time? And then if I look in my history books and I say, or I talk to the manufacturer, they say, you can expect the machine to be operating 95% of the time. That's probably pretty bad. It's likely more than that. Then I would have a I would have a load factor of 9.95.
Yes, that's more to like encapsulate machine braking in the
Machine braking, yeah, uptime. So it's just a great question. It's just a convention. Thanks. Yeah. So this makes a few other assumptions. You know, for example, it's saying that the equipment is not dedicated. What this means is, you know, the equipment can be used for many different tasks in your factory. It can be fractionally utilized. You know, if the equipment is dedicated, meaning it has only one purpose, then you must have an integer number of machines regardless of their utilization. What we mean here is that, you know, if I know I'm only going to make one part, or 1,000 parts, and my machine can make 10,000 parts a year, and that machine's going to sit idle for the rest of the time, then I'm going to have to pay more on equipment cost effectively per part. And then, as I said, this is effectively a simple line, a straight line depreciation model in the lifetime of the machine divided by the number of years. So, explain to me this chart. We go to Alibaba, we query the cost of injection molding machines. 2 years ago, but I checked and it's pretty much the same. Why do we see this trend?
That's an outlier.
Sorry?
I mean,
Yeah, I mean there is an outlier. Well, which is the outlier? This one or this one?
well, I think the one at the end possibly.
The one at the end is just a really big machine.
Okay.
This one's off the line. Trends are never perfect. But what are the physics behind this? Machine cost versus clamping force. Yes?
You're just seeing bigger equipment, bigger like hydraulics,
Yeah.
bigger stuff.
Right on. So, you know, one way that you spec an injection molding machine is the clamping force, which is related to the injection pressure, related to the part area. Right? Kind of pressure drop times area is clamping force. And yeah, if you need more clamping force, you need a bigger, heavier, a huskier machine, stronger hydraulics or electric actuators to hold the mold closed. And that's the trend that you see. And I just found it interesting when we queried this that we have this roughly linear trend between machine cost and clamping force. This is, you know, these injection molding machines that we queried are, you know, sort of more low-tech than the nice touchscreen injection molding machine that we have in our shop. But it shows this particular trend of, you know, of machine cost versus clamping force. What do you think about a milling machine? What would drive the cost of a milling machine?
Horsepower.
Horsepower? Sure.
Number of axes.
Number of axes? Yep. Anything else?
Build volume.
Build volume? Yeah. All of those are good answers. Table size, spindle speed, motor power, accuracy. And of course, there are different classes of milling machines, whether they be, you know, I would call the Prototrax a semi-CNC machine. There are fully automated CNC machines. There's 3-axis, there's 5-axis. We looked on Alibaba at with low-end, only semi-automated CNC machines and found that for that particular class of machines, there was a roughly linear relationship between machine cost and table size. Why would table size, why would build area affect the cost of the machine?
Bigger.
Bigger. What does bigger mean?
It can hold bigger parts, and it might mean that you do have a higher power motor because you're planning on taking more material away.
Yeah, great. Something else?
You also just need more material to make the bed. You need a bigger encoder. You need it to still be as stiff, even though it might have, like, you know, bigger lever arms and things like that.
Yeah, exactly. So, you know, bigger machine is stronger, has to move the part a longer distance. If you say the level of accuracy or relative accuracy is the same, it has to be made accurate over a longer distance, need longer lead screws, probably a stronger motor to drive the table because your part's going to be heavier. Perhaps you're removing more material, as you said, so that the machine frame needs to be stiffer. All those things come together. And, you know, the point is not that, you know, there's always this linear scaling, but the point is that there is a scaling according to the physics of equipment design, and if you look at machines at different classes, there'll be something that drives the cost. Same thing if you see 3D printers and you have small, medium, and large. You also have difference between desktop grade and industrial grade printers. Another reference point is these are fairly low-end milling machines. This cost, if you pick up a machine from a manufacturer in China, you go to the port and you pick it up. $35,000 for one that's about 10,000 square centimeters, so 10,000 square centimeters is a square meter, 100 by 100. If you go to the website of Haas, and this is a newer Haas machine, we have an older Haas machine in our shop, and you spec out a 3-axis vertical CNC mill, so XYZ with a vertical spindle that has roughly 1.5 by 1.3 meter area, you get a cost of $210,000. So a more automated machine, you could say more sophisticated machine costs more, and you see all the specs like max rating of the spindle 22 kilowatts, pretty good power. We were doing like 1 to a few kilowatts in our turning demonstration. Max speed 7,500 RPM, and so on and so forth. And of course, you would, if you can buy it with a different spindle, or bigger area, or higher accuracy, the cost is probably going to scale. About that. So let's talk about variable costs, and I think I'm going to speed up a little bit here. So, variable cost. First one is cost of material. This is really simple. Material cost, cost 3 part mass in kilograms times material cost per kilogram times 1 minus scrap fraction. Example, injection molding, 70% part, 30% scrap, runners, gates, etc., sprues, and that would be your total cost of material per part. Cost of raw material ranges widely, from energy materials, oils, fuels, and coal, to highly engineered precious materials, right? Coal, 10 cents a kilogram roughly, to diamond, $1 million a kilogram, and a whole lot in between. Kind of makes sense as materials become more specialized, more engineered or precious, material cost goes up. And plastics, $1 to $10 a kilogram. We talked about the cost of thermoplastic in that range. Well, they are engineered petroleum products. Point is, we take petroleum out of the earth, we refine it into plastics, we hopefully recycle it, but you have to add value by the processing. Same thing in metals, right? Heavy alloys to lightweight alloys, more out of the earth, simple processing alloys to more specialized super alloys, and then ceramics, composites, and so on. Finding the cost curve for material. I have a couple of charts in here that just show, for example, if you look on Alibaba at the cost of plastics, the cost of materials is also a function of volume. Right? If you want to pick up an order of a big quantity of plastics, 100 kilograms of PET. PET is polyethylene tetra something that's used in a lot of plastic drink bottles. You'll see it on the bottom with the recycling symbol. The cost goes down to roughly $1 per kilogram if you order a large quantity. If you look at aluminum, what do I have here? I have Alibaba's price of aluminum. If you want to pick up a minimum of 500 kilograms of aluminum rod, that'll cost you $2 to $4 US dollars per kilogram. If you want to order aluminum from McMaster, and you just need a small bit, say 1 inch diameter, 6 feet long, it'll cost you roughly $15 a kilogram. I just looked up a price and I took the density and volume and calculated that cost. Huge difference. Maybe it's no surprise, but it tells us that cost of material that we pay is a function of the volume that you bought and the availability of the material. Right? This requires you to have a shipper bring it to you from China, and this gets to you next day from McMaster, though you have to pay shipping on top of this cost. So there is a value add, there is a profit margin that McMaster gets from selling the material in the small pieces, and of course whatever company processes the material, getting it from a foundry overseas or domestically. And for something simple as a bar of aluminum, there's all these cost elements, raw material and making it, machine cost, tooling cost for the processing, and then subsequent costs in distribution and then cutting and profit margins too. Last one, overhead cost. Labor, facilities, energy, etc. The simplest one, C4, I'm just going to say that we're going to give ourselves a total cost of overhead dollars per hour and production rate in parts per hour. So if I know I say my overhead is just my labor cost, or I approximated just my labor cost. Say it costs $50 an hour to have a worker, to pay their salary, to pay their benefits and so on, taxes, and I can make 100 parts an hour with that one worker, then the cost of overhead, cost of labor per part, is 50 divided by 100, 50 cents a part. And labor cost varies widely around the world. Something we already know and appreciate, and of course as manufacturers make decisions in engineering and production, they often consider the cost of labor. We'll get to this in more detail in a few weeks when we end the class, but suffice to say that there's very high wage countries and there's very low wage countries, and as a matter of fact, even in places like China, because the standard of living is rising, there's more wage pressure on manufacturers, and manufacturers in China are widely adopting more automated factories to increase the quality of their production, while more labor-intensive production goes to even lower wage countries. Over the past 10 years or so, I've heard that the fully burdened cost of labor in your typical big Chinese manufacturing facility has gone from $2 an hour to $6 an hour. That's a huge increase. And if you have a highly labor-intensive product, a 300% increase in the cost of labor is going to really drive up the cost of having that product manufactured on a contract basis. And the Scandinavian, Western European countries tend to have the highest burden cost of labor, and U.S. is right between sort of $30 and $40. Everything goes up. It's hard to find data from the past year or two, but this shows 2010 versus 2013. China here only had the data for 2010, but I learned recently that it's currently about $6 an hour. All right, so what do we have? We have the sum of the four elements. I won't explain the equations again, but tooling cost, equipment cost, material cost, overhead cost.
Are heated until they liquefy and then injected into metal molds in which the plastic cools and plastic cools.
And of course we know this already, how Legos are made by injection molding. Our favorite video once again. And now we can think about the cost of material, the cost of tooling, the cost of machine, and the cost of labor. So what does it cost for a Lego brick to buy it? Well, we can buy a big box of Legos from Amazon, 790 bricks for $60, $59.95 last time I checked. And inside this box, there are a lot of similar bricks, and there are a lot of different bricks in bags for different colors. And, stuff that's like a window part versus a standard 4x2 post brick, another different color window part. And if I average the cost of all the bricks evenly, I say that I'm paying 7.58 cents per brick. So the question we want to answer is, simply if I'm making one kind of Lego brick, say a typical 4x2 post brick, what is the estimated cost of manufacturing, and what is the relationship between the individual cost components and production volume? Then we can reflect at the end on what Lego's business actually is, and maybe how much profit they can make. So I'm going to tell you a couple of the cost elements, and then we're going to get to the answer. So first is the material cost. And we looked up cost of high-end ABS. Most colored Lego bricks are made from ABS plastic. And we said there's a scrap fraction of 1%. The reason why we've said scrap fraction of 1% is we said, well, let's assume Lego is using a hot runner mold, and there's very little scrap. Maybe 1% even if that of the bricks are defective. So hot runner mold means there's no waste part separated from each brick. This is total material cost versus production volume, linear, right? And the answer is the material cost is $0.007 per brick, less than 1 cent per brick. And we did this based on the dimension of the volume on the previous slide. Tooling cost. What do we have to consider when it comes to tooling cost? Well, we used for this example the online cost estimator for the mold characteristics that I pointed to before. And the exact characteristics we use aren't really important. It's important for us to understand the outcome. But we had the volume of the part in terms of plastic size, the projected area, the number of cavities, and we are able to estimate the tooling cost. And the thing that was interesting for this specific example is the question of what is the relationship between the tooling cost and the number of cavities of the mold. Because of course when we discussed injection molding, and when you see in the video, we see that often Lego makes bricks with many bricks at once in each mold set. And in this cost estimator, we can get a price estimate for the total cost of the tool versus the number of cavities. So for a 1 cavity mold set, this means that it'll be about $9,000. And for an 8 cavity mold set, this means it'll be about, say, close to $30,000 or $40,000. And as you increase the number of cavities, according to the estimator, from 1 to 4 to 8, the cost goes up in a relatively proportional fashion because you need more material and you need more material removal time. And you have this base cost of making the first mold of about $9,000 for a single cavity. Now, why might this be important? In what cases might you be deciding, do I want a single cavity mold versus a multi-cavity mold? Think about the production volume.
Just how many you need to make.
Yeah, how many you need to make. So say, for example, you know that you can produce 100,000 bricks a year for a 1 cavity mold, but you need to produce 500,000 bricks a year. If you're limited to only 1 single cavity molds, then you're going to need to buy 5 sets of single cavity tooling. And you're going to have those 5 sets perhaps in more machines, depending on how quickly the machines work. If you can buy a 5 cavity mold, then you can make 500,000 parts in 100,000 cycles. And even though the tooling cost is more expensive, it's a benefit to be able to do that production more efficiently if that's your production volume. So that's the point. In this case, we estimated a cycle time for the injection molding operation. I believe it was 6 seconds. Yep, it says 6 seconds back on slide number 27. And we calculated the tooling cost per part as a function of production volume. We'll be posting a spreadsheet that has all of our assumptions and factors in it. But basically, you see that at a critical production volume of between 1 and 10 million, I think it's about 3 million parts, then there's a crossover point between having a 1 cavity mold and an 8 cavity mold. And it's based on the number of parts that you can make per year in a mold with a certain number of cavities. So if you have a production volume greater than 3 million parts per year, then it's more cost effective in terms of tooling cost per part to use an 8 cavity mold rather than a 1 cavity mold. If the production volume is lower, then you don't get any extra benefit from those extra cavities being in your mold because you're not limited by the available throughput of a single set of tooling. And when you look at pictures from the Lego factory, you see once again, yeah, they use large numbers of cavities. This is, I guess, the core mold and not the cavity mold by our definition, but same difference. Here you could make 10 bricks at the same time with this set of tooling. It also looks like it's made out of a really hard tool steel. This is not aluminum. They're producing a huge number of bricks from this tool. So here's a slide that talks about equipment cost. And the way we are treating equipment cost here is that we're saying the equipment cost is dedicated. So it means that we need to buy a machine and dedicate it to our task of molding Lego bricks regardless of the production volume. We say the machine costs $200,000. We say the depreciation is 10% per year, the lifetime is 10 years. And the number of machines that we need is determined by the required volume and production rate. So at a cycle time of 6 seconds, we can make 3.3 million parts per machine per year. In other words, per mold cavity per year. Now that's exactly the crossover point that we saw on the previous slide between the 1 cavity mold and a multi-cavity mold. 3.3 million parts per year. So if I look at the total equipment cost per year versus volume, if I have to invest in one machine, right, for minimal production, then my machine cost is $20,000 per year, 200,000 divided by 10, independent of production volume, until I reach a situation where I need an additional machine. And if I have a single cavity mold, I need that additional machine much sooner than if I have an 8 cavity mold. In fact, if I have an 8 cavity mold, I don't need that second machine until I'm off the chart, until I'm what, 3 million times 8, so 24 million. This 10 to the 7 is just 10 million. And you can also look at the equipment cost per part. Because we're investing in dedicated equipment here, the equipment cost per part goes down until you reach this transition region, and it's the same regardless of the number of cavities of the mold until you start needing to have more machines. So I skipped the overhead cost, but the overhead cost was just simply treated in terms of effective overhead cost per part made. And what do we get? Well, we get, in the case of these assumptions, that we have a cost volume curve that looks somewhat like our example of fixed cost and variable cost. We could extend the cost, the curve out to 10 to the 8 and 10 to the 9 perhaps. And we see that the cost declines relatively linearly as we pay off the fixed costs for equipment and for tooling. And then there's this crossover point, when you consider everything together between 100,000 and 1 million parts between the use of a 1 cavity mold and an 8 cavity mold. And the asymptotic cost is about 6 cents, I believe, per Lego brick. Or so I think this is the wrong chart. It reflects a previous version of the model, so I'm going to fix this because the numbers here, the crossover points and the asymptote is not consistent with what I told you before. So sorry about this, but I'll get the right one into the slides. The answers that are correct are here. These are the individual cost components: material, tooling, equipment, and overhead at different production volumes. And basically you see the following, that the material cost is always the same. I only show the cost per the third decimal place here because we're down where it matters. So less than 1 cent material cost. The tooling cost at the highest volume is 1 cent per part at 10 million parts. The equipment cost per part at 10 million parts is even less, 0.2 of a cent, and the overhead cost, according to the assumptions in our spreadsheet, is 1 cent per part. And this all adds up to a total cost per Lego brick of about 3.3 cents. I mean, according to our assumptions, it's just assumptions. We're not Lego, and we don't know how much it costs to be them. But this basically tells us that, you know, if we were to operate as Lego under these assumptions and produce a large quantity of bricks, we could make them for 1, 2, 3 cents, and if we could sell them for 7 or 8 cents a brick, we can do a pretty good business. I would bet the Lego's production cost is lower than this. It of course depends on the size and complexity of the bricks they make, but this is a fair estimate of the cost components that would come into play. Another thing I find interesting here is that the cost components are of roughly the same order of magnitude. The equipment cost at volume is the least expensive cost, and then according to our assumptions, material and tooling and overhead happen to be about the same. And this is just a graph for reference, which is the relative cost components versus volume. I don't need to explain this directly, but the formulation is it's the individual cost, C sub 1, like equipment cost divided by total cost, and they change with volume. So if I reflect here for a couple minutes, I said that the predicted cost of making these bricks is 3 cents per Lego if you operate the factory for 16 hours a day. That's the assumption we made in the spreadsheet that we'll share with you. Material could be less expensive. We assumed high-end material, yet perhaps they are need to recycle the gates and runners if they're not using a hot runner mold, and in fact they're using a 3-plate mold where they eject the runners and gates and screws and have to recycle them back. We also made the assumption of dedicated equipment, right? Because I said that we have to buy the machine, and our cost of machine only goes down, down, down at our highest production volume. In the real Lego factory, of course, they're not having machines setting idle, but what they're doing is they're constantly changing different tools into different machines, and I'm sure there are some machines that are running all the time, perhaps making the same bricks of the same color and the same size. And other machines that are swapping out tools more frequently, maybe every day, maybe every week, maybe more often than that, to make the more specialized brick geometries. So, I think that LEGO is a master of injection molding, of course, and they're probably also, masters of understanding how these costs scale with production volume and what it costs them to make a new tool set, and if they need, to make 10 million of a certain brick, and or as many as they possibly can for a long time, and they can invest in the highest quality tooling. Or maybe they're selling, Darth Vader sets for Star Wars, and they say, oh, our production volume is only 100,000, or we don't know how big the market is, so we want to make softer tooling, aluminum tooling or low-end steel tooling, and they invest in the cheaper tooling to begin until they test the market. And this constant swapping and sharing of capacity allows them to approach the asymptotic costs for the highest volume bricks. So if they can swap out tools and they can invest smartly in their tooling and share their equipment, they can produce as many bricks as possible for those asymptotic cost numbers, referring to what the cost approaches when the variable cost dominates over the fixed cost. And we're not considering other aspects like packaging, shipping, marketing, kit design. If LEGO makes a Star Wars LEGO set, they have to pay a royalty to Disney that owns Lucasfilm now, obviously, for making a LEGO set Darth Vader. And they have to pay the design time for the tooling and the testing of the molds, as well as the design time for the set itself. So there are other costs in the equation, even for something as simple as this. And to close this section, I think it's super interesting to imagine what their cost calculus is like. They surely have cost estimating tools internally that they use, and if you even look at a field of LEGO characters and the different hair pieces and hats and the different printing on their chests and colors of legs, there's a lot of different parts that they master, and each process, even the printing processes, has its own cost versus volume characteristic. All right. Are there any questions at this point? All right, so in the time we have left, I want to reflect upon a few what I call limiting cases, which will let us now step out of the mathematics of modeling cost by component and just think about how different factories work and what the driving cost factors are as reflecting the manufacturing operation and the nature of the product. So the three examples I will have is window glass, the iPhone, and 3D printed aircraft parts. And what's different among these? I think I left it blank on your slide. Well, of course, what's different is the number of components and materials you have in the product, the location of production relative to material extraction and end use, the cost per kilogram, the number of parts per year. Basically, I think that these three examples provide different extremes at what drives the cost of the product and the cost of manufacturing. And yet all of them still fall into this general definition of manufacturing being realizing value, realizing market value, value add at a sufficiently large scale. But the way that value is defined is very different in these cases, and the way that value is added to maximize the sales price is also very different. For example, in the case of 3D printed parts, we're going to think about the effect on aircraft fuel efficiency, even though the manufacturing cost is high. In the case of window glass, we're going to realize that there are other factors driving the cost, very different from the case of 3D printing. So, maybe we've already said some of the things that that are relevant here, but it turns out the process of manufacturing glass, to me, is a really, really fascinating process. It's called the float glass process for a reason we'll see in a moment. And this is a picture of the back end of a float glass manufacturing facility. It's just outside of Detroit. I visited there a couple years ago. This was in the middle of winter, one of the coldest days of the year. And this is these are the piles of earth that go into the furnace at the back end of the plant. And it shouldn't say mile here. I changed it from a quarter mile to greater than 1,000 feet because the plant continues literally a quarter mile long. The production line is straight about a quarter mile because of all the steps that are involved. Now this plant
and is exported around the world.
Same plant looks like this.
This is where we
we turn sand into glass. The furnace holds about 1,600 tons of glass. It heats up to as high as 2,930 degrees.
I was next to this furnace,
Once we
and it
start
was
a furnace
middle of
up,
winter.
it runs continuously.
It's the biggest expression of heat I've ever seen. There's like flames shooting out of the portholes in the furnace inside this building.
They turn sand into glass.
And they said it takes 2 weeks to heat up and cool down the furnace if something goes wrong, so they never want to shut it
It's a
down.
lot trickier than you might think. First, the sand and other additives are fed from a batch.
At the beginning, the production rate is, the velocity is very slow because it's a huge tower where they mix all the components.
The temperature in the batch homogeneous.
And they stir the molten glass.
Under a wheel stone, which can be raised and lowered to regulate the flow. This is the main artery, where the glass becomes what's referred to as a ribbon. This next part is fascinating. The melted glass flows onto a melted tin bath and spreads out into the width of...
So this is really interesting. This is why they call it the float glass process, and it's seriously inside controlled atmosphere, continuous sheet of glass floating on a river of molten metal. And the reason why this works is because the glass and the molten metal don't mix, and because the molten metal has a very smooth surface. So Pilkington, if you've ever heard of Pilkington Glass Company, he invented this process in the 1950s, and it enabled mass production of glass with smooth surfaces, because the molten metal is essentially a floating tool. And this process has to be very carefully controlled, and this wheel you see is actually pulling the glass, pulling the ribbon of glass down the river, which is maybe hundreds of feet long, inside a box with a controlled atmosphere, which is an inert gas like argon or nitrogen, and a little bit of hydrogen that prevents the metal from oxidizing. And they have to keep this really, really pure and clean.
The thickness of a customer's specific order. The head of the machine stretches it, while heating elements in the roof regulate the temperature and pressure. Workers monitor the process from a control room, 24/7. When the
There are
glass
control charts
exits
on the
tin
screen in
bath,
this place.
It is now about 1,100 degrees. This is the first time the glass is solid enough to break.
Natural gas
The
flames.
ribbon next enters the lair, where it rides over rollers.
And the temperature goes down
The glass
as
passes under
the process
10%.
moves forward.
Then through a laser
And then at
inspection
the end,
to
they have
ensure the
laser
highest quality
inspection,
standards.
and
Next
cutting,
is scoring.
scribing and
First
cutting.
north to south, then east to west. It passes over a bump roll, which frees the glass along the first score. Then the edge trim is knocked off
And they
and
cut it into
recycled.
panes at the end.
Workers dressed head to toe.
And then
for sitting on
another thing I found interesting is at the end,
while the giant ones
you
are
saw a lot
held by
more
robots
people than you did at
before
the
all
beginning.
these
At the beginning it was very quiet and there were just people looking in the windows and people in the control room. And at the end you start seeing workers helping stack the panes and then the processes that follow. So obviously, what's a big driver of the cost of this process? Say that again?
Heating of the glass.
Heating of glass, so energy is a big driver. What else? Raw material. So the cost of raw material is going to be a big part of the cost of the glass, the cost of making the glass. Factory cost, of course. I mean, everything does make an impact, but like that furnace and that float glass line were tens of years old, and these plants, this plant had 2 lines in parallel, and it made, what do we say, each line was tunable between 500 and 800 tons a day. That's crazy. Earth going through this thing at an impressive rate, even though, it seemed slow when you looked at the video. So the process has these stages, from the input material to the finished glass product. And a couple more interesting things. One is, when I said, oh, they have a laser inspection, and then they cut the glass into pieces, break it up, they had a defect specification. They said, well, on a particular day or a particular week, we're making glass for a certain customer, like we're making it for Ford, or we're making it for shower doors or something. And each customer or type of glass had a thickness specification and had a defect specification. Like you couldn't have a void in the glass that was bigger than like 0.1 millimeters. And they had, laser inspection equipment that would determine whether a certain pane of glass met the spec. And if it didn't meet the spec, a robot would come in, pick it up, turn it 90 degrees, and drop it down in a trench. And it went all the way to the back of the line. And it got mixed into the new product. And this did 2 things. One, it was like in situ recycling. Second, they said it kept the feedstock more uniform because the process changes if they have 2 significant variations in the input feedstock. And third, it was like a different philosophy on quality. Like clearly they couldn't afford that, this scrap fraction was huge, but 10 to 15% was okay. So they could allow a certain level of defects because they were able to send the product back to the beginning. The other thing is the reason I got to know this company is because we were working with them on a research project to develop new coatings for glass, specialized carbon films for coating the glass, and how they add value to the glass is actually after the end of this line at the end, where they have a bunch of machines that deposit very, very thin films on the glass, and as we'll discuss when we get to electronics, every piece of glass you buy that's functional for use in a device like a touch screen or even on a window has a large number of thin films of different materials, metals and oxides and ceramics, just like you see on the coating of a machine tool, of a milling tool. And this, for example, in the case of window glass, is engineered, highly engineered to allow maximum light in, but allow minimum heat in. So has a spectrum that is hopefully blocking the IR, but allowing the optical light in. And the innovation in glass manufacturing is not only in the composition of the glass for things like tough shatter-resistant glass for phones, but also the coatings on the glass to make the optical performance and other performance better. So even in this industry where things are very raw material intensive and the cost of making the glass itself is driven by raw material and energy, there's also the ability for the company to add functionality, and that's what's differentiating their products. So the next example I have is the iPhone, and I'll just show you a couple slides here. Of course, the iPhone is one very popular and global electronic device. Numbers a bit mixed up here, but this company plots the data that Apple releases and basically says that in 2016, so far, Apple's fourth fiscal quarter has ended. If you sum up all the Apple iPhone models sold around the world, new models, you get, this is greater than 200 million iPhones. So what does this mean for Apple? Well, of course, they can invest huge amounts of money in design and engineering and in contracting manufacturers to ramp up their production. It also means they have to be really on the ball when they announce a new product. I think this is referring to the iPhone 5 in 2014. 10 million new phones sold in the first weekend. You really have to prime your supply chain if you sell 10 million phones in the first weekend and you need to reach the customers soon. So iPhone, like any electronic device, like the one I held apart in the beginning, consists of many different components, sub-assemblies, CNC machine parts, touchscreens, so on and so forth. The point I'll make here, and the point we'll get to when we talk about electronics, is this becomes a different way to think about cost and scaling of cost. If you look online and you search like iPhone manufacturing cost analysis, while Apple doesn't say how much it costs to make the phone, that's very proprietary, secret information to them, consulting firms and so on that do analytics of this will estimate like what it costs Apple for the display, the battery, the camera, the connectivity, and Apple invests a lot of money in working with suppliers to build components of the phone to their specifications. So Apple itself does not own many manufacturing facilities, whether it be for components or for assembling the phone together. They contract companies for all parts of that. And they try to exert as much control as they can over the specifications, over the price. They apparently drive a really, really hard bargain. But when you look at the cost structure of a device like the iPhone and the Fire tablet and your Samsung phone or other one you might have, it's actually quite modularized in terms of the costs of the individual major components, like the display and the touchscreen, because that's arguably the most valuable interactive aspect of your phone, might cost Apple in this estimate for the iPhone 6 $40. And if you look at the estimated cost of final assembly and testing, putting the modules together, it ends up only being about $10. And this estimate of the total cost of manufacturing was $200. And the way that the smartphones are sold is changing per month versus upfront cost and contracts and so on. But when this, I think in the case of the iPhone 6, it would be like $200 if you got a 2-year contract. If you want to buy it unlocked and do whatever you want, it might cost $600 or $800. It says that Apple makes a huge amount of money on each piece of hardware because they're either paying them the profit directly or they have negotiation with their with the cell phone carriers to have a kickback from the price you pay every month for your voice and data plan. And the cost of electronics becomes driven by the cost of the finest components that get put into each circuit board and each element, but also the modular cost structure of integration and assembly. And Apple's manufacturing cost, if you will, that they directly have control of is in the end quite small, which I find to be another interesting limiting case. And, you know, we could say that as the volume of the iPhone advanced, the production volume, they could be more sophisticated, or their suppliers could be more sophisticated in using automation, CNC machining to advance the design, the lightness, the functionality of the product. And as we discussed in the case of machining, I don't bring this in as like a new kind of example, but just a reflection that, you know, when you think about cost now, I showed quickly in the machining lectures, you can optimize machining for cost or time, and you have like tool life and tool wear and tool change time. And here's another level of cost versus volume that could be considered. So if you're machining 200 million metal cases a year, then you're probably doing this calculation at the finest detail to understand what's the rate of, you know, what's the rate of machining one, what's the cost of the tool, what's the cost of my machine tool, and then a Foxconn, that's their main contract manufacturer, I've heard, you know, drives a hard bargain with the suppliers of their machine tools. And, you know, if a company sells CNC milling machines to Foxconn, they're going to sell 5,000 CNC milling machines. So they're going to try to find the best deal for the performance that they want, and you're going to have, again, a cost volume dependency, not only on machine size and specs, but also the number of machines that are requested. So I don't think I'm going to get entirely to the rest of the slides that I had, but I want to make a couple quick points. The first is, if you look at the charts on slide 70, you see an interesting reflection between profits of different companies and like what's behind the scenes in terms of their cost structure. Like Apple has a huge profit margin relative to consumer product companies. Profit margin means 25% of their net income, the money they take in from their customers, like us, relative to, their revenue, the money taken from their customers, the blue one, compared to the net income, is a ratio of 25%. And that's really, really big when you consider not only the manufacturing costs, but marketing, distribution, sales force, R&D, and so on. If you look at Procter & Gamble, big consumer products company, they make laundry detergent and a lot of other consumer products, Gillette razors, for example, they do pretty well, but their profit margin is essentially half of what Apple is. If you look at Amazon, Amazon has just started to turn a profit, but you know, Amazon's one of the most valuable companies in the world. If you look at their stock price, they make basically no money. And it's actually a matter of their corporate strategy. If you read about it, that the management of Amazon, including the founder, have sought to invest heavily in infrastructure, in their back-end website, all their distribution centers. Now they're buying planes to convey stuff across the world, and they're starting to turn a slight profit, but their bet is they want to get as many customers as possible for their products and services, and then it's not like they're going to start, charging higher prices, but what they're going to do is they're going to reap the benefits of that capital investment, of that long-term investment. And if you look at the last example as 3D printing, I was going to say, and you can just read the slides on your own, that the case of, for example, metal 3D printing, which is of huge interest to aerospace companies and so on, is still a losing case. If you look at the cost of doing the printing itself, the cost of the metal part will be crazy, a few dollars per cubic centimeter. This is a recent estimate that says $3 per cubic centimeter. But if you look at the value, like even replacing, if you sit in the exit row or the bulkhead row on an aircraft that has TV screens, you have to take the screen out of the armrest. And there's only a few dozen of these parts on any plane. Example being a 747. This study did. It basically said that it'll cost you $2,000 to replace this monitor support arm by a 3D printed optimized part versus the standard machine part. That's really expensive for something that's maybe this big and made out of, I don't know, aluminum. But each of these parts over the lifetime of the plane will save $22,000 per part. And the effective value there is nearly $1 million over the lifetime of a plane. So you have companies going in and replacing parts, these mundane parts that don't really affect how the engine performs or how the wings deflect, but having an attractive value proposition for using 3D printing to create value. So not always is the value in the sales of the product, but it's in the long-term use. I have an initial slide just concluding what I think we learned, and we'll conclude here for today. Next week we start talking about manufacturing systems.